Welcome to Lesson 63. In your investigation, you have solved the first related rates problem. And essentially, related rates problems help you to analyze the effects of how the change in rate of one variable has on the change in the rate of another variable. In this video, we're going to go over a few examples that show you the steps to solve related rates problems. You'll find a structure, hopefully, when we deal with these questions and how you can assign variables and set up relations using the math you have learned before. Let's begin. Example 1. A ladder 5 meters long is leaning against the vertical wall. If a person pulls the bottom of the ladder away from the wall at 0.5 meters per second, how fast is the top sliding down the wall when the bottom is 3 meters from the wall? And also in part B, the top is 2 meters above the floor. I have outlined a few steps here, which you can apply to most of these related rates problems that you will be solving. So let's follow these steps now to find how we can figure out the answers to example 1. We will begin by drawing a diagram. The ladder is 5 meters long, leaning against the wall. So let's put in the ladder, label 5 meters. Step 2, assign variables. Since we are mentioning how quickly this ladder is slipping away from the wall, we need something related to what's happening near the ground. Let's call this distance between the ladder and the wall x. Therefore, the rate of change here, dx by dt, can be labeled as 0.5, and we can write this down in step 3 as well. We are interested in something related to the height. How high above the ladder, above the ground is the ladder? So let's call the vertical distance y. And the rate of change, dy by dt. It is unknown, so let's put question mark here. In step 4, we will be writing an equation to relate these variables. Since we have a right triangle with 2 legs and a hypotenuse given, naturally, we can use the Pythagorean theorem. X squared plus y squared equals to 25. Let's turn these into rates of change. We are now going to differentiate this equation with respect to time. So I have x squared becomes 2x. Using chain rule, this is dx by dt. Plus y squared. Chain rule again. First, we differentiate 2y, and then dy by dt equals 25 turns into 0. What we can do now is to substitute any values to give the rate of change and variables. And then we can solve the problem. One thing that we can include in the question is dx by dt we know is 0.5. So let's multiply this. This is still 2y dy by dt equals 0. So I have x plus 2y dy by dt equals 0. In other words, dy by dt is negative x over 2y. So this is a general equation. Let's apply this to solve part A and part B of the problem. Part A of the question, if you recall, asked that, well, how fast is this top sliding down the wall when the bottom is 3 meters from the wall? This implies that when x is 3 meters, what is dy by dt? Our equation still involves the y variable. So let's find the value of y when x is equal to 3. And it is 3 squared plus y squared equals to 25. So y must be 25 minus 9, which is 4. Okay, let's substitute this into the equation. Now we know dy by dt is negative 3 over 2 times 4, which is negative 3 over 8. There we go. So this is how quickly the letter is descending, so the negative sign, right? When the letter is 3 meters away from the wall at the bottom. Part B, we can do something very similar. Part B, the top is 2 meters above the floor, so y is 2. X squared plus 2 squared is 25. X squared is 25 minus 4, 21, so square root of 21. As a result, dy by dt in this scenario is negative root 21 over 2 times 2, or negative root 21 over 4 meters per second. Let's go over example 2. 2 cars approach an intersection. One traveling south, so let's start making our diagram, going south, at 40 kilometers per hour. So I'm going to call this dy by dt negative 40. And then there's a second car going west at 70 kilometers per hour. So let's call this dx by dt negative 70, because the arrow is going to the left. How fast is the distance between the cars changing when the westbound car is 4 kilometers away and the southbound car is 3 kilometers away from the intersection? So let's pretend that this is their current distance from each other. I'm going to use s instead because I don't want to mix up the derivative d by dt with another variable d. Until these cars move closer to the intersection when the westbound car is 4 kilometers away and the other one is 3 kilometers away, like here. Okay, we can see that the distance between the two cars is shrinking. Using the diagram that we have, we can say that the distance squared is x squared plus y squared. Is Pythagorean theorem again. Let's differentiate implicitly. I have 2s ds by dt, the rate that this distance is shrinking, is equal to 2x times dx by dt plus 2y dy by dt. Let's substitute the numbers that we know so far. At the moment, the y direction is 3 kilometers away from the intersection, and the x direction is 4 kilometers from the intersection. S must be 5 kilometers from the intersection because of Pythagorean triplet, 3, 4, 5 triangles. We can also substitute the speed of these cars. So here we go. 2 times 5 ds by dt is equal to 2 times 4 negative 70 plus 2 times y3 dy by dt is negative 40. Let's simplify that. This is, I'm just going to cancel the 2's. It's too redundant. Okay. And then I have negative 280 minus 12, 0. And then ds by dt all over 5. 400 divided by 5. Negative 80 kilometers per hour. So let's take a look at the signs of the variables and the rates of change that we have used in this question. Assume that south is negative and west is negative. The speeds have negative signs. ds by dt ends up being a negative value, which makes sense because, as we said, the distance between the two cars is actually shrinking. The negative shows a decrease. But how come I use 3 and 4 positives when I sub in x and y? Well, that's because the position of the first car is 4 kilometers to the east, right? The positive direction from the intersection, and 3 kilometers north of the intersection. So that's why 4 and 3, they are positive. Example 3. Oil that is spilled from a ruptured tanker spreads in a circle. The area of a circle increases at a constant rate of 6 kilometers squared per hour. How fast is the radius of the spill increasing when the area is 9 pi kilometers squared? All right, let's begin with a diagram. I know my diagram won't be perfect, but that will do. So here is the circle, and oil is spreading. So basically, after a certain time, the radius of the oil spill will get longer. Okay. And then we can mark the radius on the circle like that. And the area is increasing at a constant rate. So we can write down dA, change in area over time, is 6 kilometers squared per hour. And then we're looking at how fast is the radius of the spill increasing. So we're interested in dr by dt. When the area is, is 9 pi kilometers squared. All right. So let's start by establishing a relationship between area and radius. We know that area is pi r squared. If I differentiate this with respect to time, dA by dt, pi is a constant, 2r is what I will get. So I'm going to write 2 pi r dr by dt. In order to solve this question, I need the value of r when the area of this new circle is 9 pi. So let's do that first. Since area is pi r squared, when the area is 9 pi, the radius must be 3 kilometers. Okay. So let's substitute this information back into the question. dA by dt is 6 equals 2 pi times 3 times dr by dt. As a result, the radius is changing at a rate of 1 over pi kilometers per hour, which is roughly 0.318 kilometers per hour.